Okay, so in the last class we defined the language for first order logic or the syntax of first order logic, and today we want to look at the semantics. Now, there will be two aspects of semantics of first order logic. One is what we can say is denotational, which will ask the questions what does the sentence mean, as opposed to propositional logic, where we just that a formula stands for a sentence. A propositional atomic proposition stands for a sentence, and P and Q stands for P is true and Q is true, and so on and so forth. But in first order logic, we may want to really say what are we talking about. So, are we talking about men and mortality and honesty, and are we talking about numbers and some properties of numbers, prime numbers or even numbers, odd numbers. What does a sentence mean? That is one aspect of the semantics. Then the other aspect that we are already familiar with is truth functional. Which is basically asking the question, is the sentence true? So, we look at both these aspects. Now, remember that the language of first order language, in fact, the language is defined by the three sets. Okay. So, instead of using those complex characters for that, we will just use the terms R, F, C. R is a set of relation symbols, F is a set of function symbols, and C is a set of constant symbols. Once you choose that set, these three sets, then you have defined a first order language, and of course, you have also defined, you have at some point made a choice about what are the logical connectives that you are going to use essentially. So, we will assume for the moment that we will use all the unary and the binary connectives, and when we talk about proof systems, then we will restrict the set of connectives to a smaller set. So, for example, when we come to the resolution method, we will say that the logical connectives are just not, and or, and so on. Yeah. So, we had these three sets R, F and C, and we had the set and the set V. So, I am just using simple characters here. So, these are variables. So, these are relations, functions and constants. And then we constructed terms out of this language, and then we constructed formulas. Now, the semantics or the meaning of first order logic is defined in terms of a domain. And we say that we interpret the expressions, the terms and the formulas and the sentences over a domain essentially. So, we will talk of an interpretation I, which is made up of a domain D and a mapping, which we will also call I, which is the interpretation mapping. And we will basically be able to interpret every sentence, every formula in terms of a domain essentially. So, we have a language And now, we are saying that we will define the semantics in terms of a domain D. So, a domain is basically also known as a universe of discourse, which is a set of elements. So, we will define an assignment function A, which will map the set of variables V onto the domain D essentially. So, we can choose, just like in propositional calculus we choose a valuation function which mapped every propositional symbol to a value truth or false. In this case we are now saying that to every variable in my language I can map it to an element of the domain essentially. It is like saying that for example, x is mapped to 4 or x is mapped to 5 or x is mapped to Suresh essentially. So, we can talk about the meaning of sentences under different assignments essentially. So, every time we choose an assignment function A, it means that for every variable in my language. So, I may have x 1, x 2, x 3 some number finite number of variables. I am saying that this is what they stand for in the domain. Everything that we are talking about in FOL semantics is going to be with respect to this domain D essentially. Then we have the interpretation function I, which does the following, that it maps every constant to D just like a variable. The interpretation is telling us what does this particular constant stand for. It is not something which is a variable. So, assignment is used only for variables. It maps every function symbol to an appropriate function, which let me write as follows: d raised to n to d. This is some notation which I am kind of inventing on the fly. So, essentially what we are saying is that every function symbol in my language will be mapped to some function in the domain, and a function in the domain of arity n is basically a mapping from d raised to n to d essentially. So, for example, the sum, if I write sum, then it could be mapped to d square to d. It takes 2 arguments and give me 1 argument. The one it returns 1 argument, and that argument is belongs to the domain essentially. It is a function from elements to domain. So, the constant could be, for example, that a symbol, for example, z could map to 0, and then we map every predicate symbol to a relation which we will call as P I, which is a subset of d raised to n. Again, this is non-standard notation. So, essentially every predicate symbol will map to a relation on the domain. So, for example, I may have a predicate symbol called brother, which has arity 2. It will map to d 2. It will be it will map to a symbol which, let me just call it brother I, which is essentially a subset of D cross D or a subset of D square essentially, because the brother relation is a binary relation and it relates two elements of the domain. So, it is a, and the relation will actually be an enumeration of all those elements which are related by the relation brother and so on and so forth. So, for every constant C, the interpretation of that constant will be its image in the domain, which we will denote by C raised to I, where this I is the interpretation function. Likewise, for every function, its image under the interpretation mapping would be something that we will simply call f raised to I, and likewise for every predicate, its image in the mapping would be a predicate name in the, or relation name in the domain essentially. And this p raised to I will be a subset of D cross n. This f raised to I, the function would be a function from some n variables to one variable, and the constant will is like a function of 0 variables essentially.
So, R C and F are mapped with interpretation, but R is not mapped. That is what she is trying to ask.
Oh, okay, okay. So, this should map R to, is that what you are saying? Okay, thanks. So, we have these two mappings now. So, given a language L R F C, we have an interpretation which is given by a domain and a interpretation mapping I, in which every term is mapped to an element of D, which we write as follows, that if the term is a variable V belongs to the set V, is mapped to its image, which is given by the assignment, which we will write as V A, another assignment A. Every constant is mapped to C I. Every term belonging to T is mapped to, okay. So, let me just define that again. So, if the terms are variables and constant, then they are simply, the mapping is defined by the assignment function and the interpretation function. If the term is of the kind f of T 1, T 2, T n, then that is mapped to the function symbol which is interpreted by I by the terms T 1 which is mapped by I and A. So, remember that the term can be either a variable or it may have variables, it may have constants and so on. So, we have to use both the mappings T 2 I A, T n I A, where this notation T 1 raised to I A stands for the fact that the term is interpreted under the mapping, the two mappings that we have, the assignment mapping which maps variables to elements, and the interpretation mappings which tells us what do we mean by a function name and what do we mean by a constant name and what do we mean in this case only function and constant names essentially. We have already said that the relation symbols are mapped onto. So, let me write that here. Formulas are mapped to relations on the domain of appropriate arity and so on and so forth essentially. Okay. So, let us look at the truth functional aspect of this thing. And remember that truth assignment is done only to sentences of the language essentially. So, a formula like for example 2 plus x is equal to 7 has no truth value. So, it is not a sentence, right. Why is it not a sentence? Because it has a free variable which is x, it is not quantified by this thing. So, it means that you cannot assign a truth value to this sentence essentially. I mean, it really depends upon the assignment x essentially. Whereas, if I had a formula like there exists an x 2 plus x is equal to 7, then it is a sentence, or if I had said for all x 2 plus x is equal to 7, that is also a sentence, because now the only variable in my formula is x and that is quantified in both the examples that we have. And it turns out, as you know, that in this example this sentence must be true and this example this must be false. And we will shortly define this how do we arrive at this mapping essentially. But if you look at it informally, the first formula or the first sentence is saying that there exists an x such that 2 plus x is equal to 7 and therefore, the sentence must be true. The second formula is saying that for all x 2 plus x is equal to 7 and therefore, that formula must evaluate to false essentially. So, we want to now come to a formal definition of how do we arrive at this truth functional semantics. So, as before, when we talk about truth semantics, we are talking about an assignment or a function which will map the sentences to a set which, as before, we will use the term T and F. So, true formulas and false formulas essentially. So, how do we do that? A formula. So, let us first talk about atomic formulas. A formula like T 1 is equal to T 2, which is an atomic formula, is true, which means it is mapped to this symbol T if the interpretation or the image of the first term both under interpretation and mapping. Remember that this term may have variables inside essentially. Well, actually if it has variables inside, then it will not be a sentence. So, we will just talk about the interpretation function here. So, the term under the interpretation I is same as a term 2 in the interpretation I. So, as an example, we can say that 3 plus 4 is equal to 7 essentially, where 3 and 4 and 7 are, let us say, constants in my language, and the meaning of constants is determined by the interpretation function, which correspond to the numbers 3 and 4 and 7. So, you must distinguish between numbers and their representation. What we are talking about in the language is only the representation, and we are saying that if the two elements are the same, then this thing. Or if I say PM India is equal to Modi, where PM is a function which takes a country and tells you who is the prime minister of that country. Remember that terms point to elements of the domain, and functions basically are defined terms, and Modi is a constant. So, this sentence happens to be true at this particular moment essentially. Then an atomic sentence of the kind P under an interpretation I with some terms. Actually, to be more kind of complete, we can avoid our restriction to the set of sentences, but instead we will say to the set of formulas. So, we can even still talk about formulas being true or false, which means that my original notation, which is both under an interpretation and assignment is true or false essentially. So, which means that a formula like 2x plus 7, 2 plus x is equal to 7 would be true under some assignment, but it may not be true under some other assignment. So, in the assignment in which x is mapped to 5, that formula will be true. So, we can essentially talk about the truth values of formulas also, but when we talk about the larger family of formulas, then we have to also talk about the assignment function essentially. When it comes to sentences, we do not need an assignment function because there are no free variables, but if there are free variables, then we have to consider an assignment into place. So, we will do that here as well. So, atomic formula with a predicate symbol P or relation symbol P would map to true if the tuple that we form T 1 I A, T 2 I A, T n I A belongs to the image of the relation symbol P I. So, we are still talking about formulas in general essentially. Then logical connectives are treated as in propositional logic, which means the semantics of and, or, implies, negation are treated as before essentially.